Our next speaker is Emily Nardoni. She's going to tell us about the dimensional reduction of generalized symmetries.
Okay, thank you to the organizers for this very nice conference and inviting me to speak here. And today I'm going to talk about some work that I did this spring with my really great collaborators, Matteo Sacchi, or Sela, Gabby Zafrir, and Yunchin Zhang. Okay, so tracking symmetries along renormalization group flows is, of course, a very important but often very subtle problem. One way that it's subtle is that symmetries can be accidental or emergent at low energies in a renormalization group flow. This is totally ubiquitous. Sometimes we have some tools like duality that can help us get a handle on this problem of accidental symmetries, but in general, it is not possible to completely rule out this possibility of accidental symmetries in renormalization group flows. Another way that this problem can be subtle is that symmetries can trivialize. So for example, maybe the operators that are charged under my symmetry become massive and are integrated out at low energies, and so there's nothing for my symmetry to act on, for example. Now, in this case, 't Hooft anomalies can often provide a very powerful tool to rule out this possibility of symmetry trivialization. Of course, if my 't Hooft anomaly for a symmetry survives to the IR, then some sector of the theory must reproduce the anomaly. So in this talk, we're going to be concerned with quantum field theories that are related through dimensional reduction on some compact space. And here we have some well-established tools for tracking 't Hooft anomalies of quantum field theories through dimensional reduction using, so for a d-dimensional quantum field theory, the d+1 dimensional inflow action, or the related d+2 form anomaly polynomial, integrating or reducing my anomaly polynomial, for example, on my compact space is going to, in general, give me some contribution to the anomalies of the lower dimensional theory. So of course, there's some immediate fine print to address with this sort of statement. First of all, just to comment or provide a warning, of course, this procedure generically fails to capture accidental symmetries in renormalization group flows. In some examples, we can account for this in other ways, but the more precise statement is that this sort of reduction procedure is going to yield the contribution to the 't Hooft anomalies of the lower dimensional theory that are manifest from the higher dimensional one. Okay, so it still provides a good, robust way to probe at least sectors of 't Hooft anomalies of the lower dimensional theory. Furthermore, just to comment, of course, here I'm writing some anomaly polynomial, which is valid for continuous chiral anomalies in even dimensions. But really similar tools I want to emphasize have been developed or are being developed for generalizations, for general dimensions using the inflow action to describe discrete symmetries, to describe generalized symmetries in string theory across dimensional reduction, to which I'll refer you to the very nice talk yesterday by Iñaki, and so on. But for our purposes today, it is sufficient for me to just write anomaly polynomials everywhere. Okay, so the goal for this talk is we want to track a class of generalized symmetries across renormalization group flows between quantum field theories that are related by dimensional reduction. I'm going to specify precisely which generalized symmetries we're going to be interested in and say something about. There are going to be some types of higher form, higher group, non-invertible symmetries. And my focus is specifically going to be on four-dimensional gauge theories whose generalized global symmetry structure can be traced to gauge global mixed anomalies. And I'll tell you exactly what I mean by that on the next slides. And even more specifically, in this talk, I'm going to focus entirely on 4D gauge theories compactified on a two-sphere. So you can see our paper for our comments on the S1 case for three-dimensional quantum field theories. And so the punchline of the talk is that we're going to be able to characterize the imprint of the four-dimensional, in this case, in this talk, generalized global symmetry structure on the symmetry structure of the lower dimensional quantum field theory. And as this introduction is probably emphasizing, anomalies are going to be a powerful tool for characterizing these results. Okay, so first let me tell you what arena we're going to be working with. And so specifically, let's work in the arena of four-dimensional gauge theories with some one-form, U1 one-form magnetic symmetry. So by this I mean the one-form symmetry that acts on the tuft lines associated with some U1 part of my gauge group. So you can have in mind like a U1 or a UN gauge theory, for example, in 4 dimensions. And so really the case study to keep in mind, which will exhibit these features that I'll mention, is, for example, 40n equals to 1, SQCD, with NF fundamental and anti-fundamental chiral superfields, and with gauge group UN, where the UN is arrived at from the SUN case by gauging the baryonic U1 baryon number symmetry. So this is the symmetry under which like the quark and anti-quark chiral superfields have charge like 1 over n and minus 1 over n. And so in this case study example, I'll be referring to this U1 baryon number plays the role of this U1G part of the gauge group associated to my magnetic one-form symmetry. Okay, so let's consider 4D gauge theories of this type that have, in particular, a two-group extension of some flavor symmetry or some flavor symmetries in the theory by the magnetic one-form symmetry. And so say that I have a U1 flavor symmetry in my theory that's extended by the magnetic one-form symmetry in the two group, then invariance of the action okay, I should say there are various ways to understand the manifestation of the two group in the theory, and these were discussed in this very nice paper from a couple of years ago. One way is that the invariance of the action under background gauge transformations of the two sets of background fields for these symmetries mix, so that the mixing is characterized by this integer kappa, which is the integer that's going to characterize this two-group structure. This can also be seen as the fact that the invariance of the partition function implies this non-conservation, well, operator-valued non-conservation equation for the U1 flavor symmetry current, which leads, which manifests as this gauge flavor type anomaly. So in my 6-form anomaly polynomial, it can be written like this, with this, again, this integer kappa playing, showing up as my anomaly coefficient. And so in our SQCD case study, there is a two-group that involves the non-abelian SUNF left and SUNF right global symmetries. And I haven't written it on this slide, but it's totally straightforward to generalize these equations from abelian to non-abelian symmetries and also to discrete symmetries and so on. Okay, furthermore, we'll consider four-dimensional gauge theories that have a so-called non-invertible chiral symmetry. And so these are non-invertible symmetries of the type that were studied first by these papers from, I guess, 2 years ago now. And so the setup is that we have some gauge theory that has a chiral U1 flavor symmetry with an ABJ anomaly. And the ABJ anomaly seems to break my flavor symmetry to some discrete subgroup. Let's call the order of the discrete subgroup K, so it's to some ZK, where K is an integer. So the ABJ anomaly, of course, manifests as its own sort of current non-conservation equation, or can be captured by this flavor gauge type anomaly in this language, where the anomaly coefficient is characterized by this integer K. So the observation from these papers was that, in fact, in many cases, a larger non-invertible symmetry might be preserved, where I preserve not just chiral rotations by integer multiples of 2 pi over k, but by multiples by any rational number times 2 pi over k, so times some p over q, where GCD p and q is 1. And so this is some like Q mod Z type non-invertible symmetry labeled by this integer K. So the discrete invertible part of this non-invertible symmetry is the ZK. And so in our SQCD case study that we're following, it's the U1R symmetry that becomes non-invertible in this fashion. It has an ABJ anomaly that appears to break it to Z2. But in fact, you can see that this Q mod Z type non-invertible symmetry is what's preserved. Okay, so to summarize these last couple of slides, we've seen that generalized symmetries, some generalized symmetries are signaled by mixed gauge flavor anomalies. So these types of non-invertible symmetries we're focusing on, and this sort of two-group structure. And so the question to ask, or a question to ask, is can we track these anomalies and these structures across compactification? The first response to this might be a warning, because of course, gauge symmetry is not a symmetry, it's a redundancy. Gauge anomalies, I would think, are not physical. And of course, gauge symmetry can be different in different dual descriptions across our G-flows. So you should be very worried about this idea of tracking these sorts of gauge anomalies across compactification. However, the answer for these structures is in fact yes. The reason it's yes is because really this sort of reduction, this naive reduction of these anomalies in compactification, giving the right answer, is more aptly understood or more properly understood as the reduction of this generalized global symmetry structure from the higher dimensional theory to the lower dimensional theory. And so really, like at least in our paper, we explore complementary perspectives on this question, and you can see that this sort of naive reduction of these anomalies gives completely consistent results with the reduction of the background fields on the compact space, with the direct reduction of the topological symmetry operators implementing my participating flavor and one-form symmetries, and so on. So now I will tell you some of the lessons, or I'll at least summarize for you some of the lessons we learned from reducing these types of generalized symmetries from 4D to 2D on a two-sphere. So let's say a little bit more about the setup. The first step is to think what happens to our magnetic U1 one-form symmetry. And so we're going to consider some situation where we put our 4D theory on the sphere, and we're going to thread flavor and or gauge flux on the sphere, and then take the limit that the volume of the sphere is much smaller than the volume of the 2D spacetime, and we get out some two-dimensional quantum field theory at the end of the day. And so just first some comments. So first of all, why might I put flavor flux on the sphere? And of course, like one reason I might want to do this is maybe I'm considering some supersymmetric example, and I want to preserve supersymmetry in lower dimensions, and so maybe I want to twist with some R symmetry for my topological twist. Okay, but to be clear, our methods don't require supersymmetry, but in examples where I can compute things, this might be something I want to do. And another comment is about this idea of taking fixed gauge flux. Is that in general, in these types of compactifications, we really expect, as was emphasized especially in this paper, to get a direct sum of two-dimensional theories that are labeled by their integer-valued gauge flux. But these different sectors are actually superselection sectors that have zero overlap with each other, even at finite volume of the 2D space-time. So these really define different universes of my theory. And so we can think of expanding, or we can consider expanding in one of these fixed gauge flux vacua at low energies and ask, what do we get? What 2D theory do we get when we expand about one of these vacua? And so this is the sort of scenario we're going to consider. And so what happens to our one-form symmetry? Well, a priori, our 4D one-form symmetry should reduce to a one-form symmetry in 2D, as well as a minus one-form symmetry, which does not play a role in this discussion. But in a vacuum of fixed gauge flux, this one-form symmetry will evidently trivialize. There are a few different ways to see this. One way to see it is by directly looking at the topological symmetry operator that will generate the would-be one-form symmetry in 2 dimensions. And you can see that it's evidently, it just goes to a constant in one of these fixed flux vacua. So I don't have a dynamical topological symmetry operator anymore to implement my symmetry. Okay, so we said that in these classes of examples, we generically expect the one-form symmetry to trivialize in 2 dimensions. However, the non-invertible chiral symmetry and our 2-group structures both really critically depended on the existence of this one-form symmetry. So you might think that these structures should also trivialize or as well, or not be present in 2 dimensions as well? And is there anything else we can say? And yes, there is still more we can say. And so, in fact, we can see that these 4-dimensional generalized symmetries, even if the generalized part of the symmetry structure does not survive to the 2-dimensional theory, it still leaves an imprint on the symmetry structure of the theory. So, for example, let's take the 2-group structure in 4D and think about what happens when we reduce it in these cases of fixed gauge and or fixed flavor flux. So if I reduce it in the case of fixed gauge flux, what you can see, so here I'm just writing formulas which are nice for the slide as to what you can evidently see by reducing my anomaly polynomial, but I want to really emphasize that the answer you get by this naive reduction really matches with the exact right coefficients, the answers you get from these other perspectives, reducing the background fields, reducing the topological defects, and all of those details, of course, appear in our paper. So in the theory with fixed gauge flux, mg, I in fact get a 2D Tüft anomaly, so a contribution to the Tüft anomalies of the 2D theory, and the Tüft anomaly coefficient depends both on my 4D 2-group parameter kappa and on the value of the gauge flux. I can also consider this case where the flavor symmetry that participates in the 2-group gets some flux on the 2-sphere. And in this case, you can see that this term reduces to an ABJ anomaly or a gauge anomaly in 2 dimensions. And so what this gauge anomaly implies is a symmetry breaking pattern for the associated U1 symmetry in the 2-dimensional theory. So we get a symmetry breaking pattern to some discrete subgroup where the order of the discrete subgroup depends both on this integer kappa that labeled the 4D2 group and on the value of the flavor flux that we were threading. What about the non-invertible chiral symmetry? So here we don't want to consider flux for a part of the non-invertible flavor symmetry because that would just give like a gauge anomaly in 2 dimensions, and so we won't consider that case. But in the case where we consider a sector of fixed gauge flux and what happens in 2 dimensions, again here we see a gauge anomaly in 2 dimensions, and this implies a symmetry breaking pattern of what was the non-invertible symmetry, this Q mod Z symmetry in 4 dimensions, to an invertible discrete symmetry in the 2-dimensional theory, whose order depends on, or whose order is this integer k, which labels my non-invertible symmetry in 4 dimensions, and this value of the gauge flux. So indeed, we didn't expect to get the non-invertible symmetry in 2D. We expected it to become invertible or something. And indeed, we get just a simply invertible discrete symmetry in 2 dimensions. In the special case that we look at a sector fixed gauge flux with gauge flux equals to 0, we actually, you can see, will realize the full Q mod Z from 4 dimensions, but not as an invertible symmetry, as an invertible symmetry. So all of those chiral rotations by like rational multiples of the 2 pi over k will realize invertible symmetries in the 2-dimensional theory. You might expect that generically this should enhance back to a full U1, and at least in examples we can argue that this does indeed happen. Okay, and so just one comment is that we've seen already in this conference a couple of talks on the symmetry TFT and a very nice unified perspective on these results that I just summarized on the last couple of slides comes from taking the symmetry TFT for these classes of non-invertible symmetries with this 2-group structure that was proposed in these papers, and reducing the symmetry TFT down on the 2-sphere with the various fluxes to 2 dimensions. And in a unified way, you can really get out exactly all of these comments about the symmetry breaking pattern and Tüft anomalies of the lower dimensional theory from this perspective. So that's all I'm going to say about that, but just a comment if you're interested. And so I'm going pretty fast. Okay, so finally, I'm just going to review for you the results of our case study of 40n equals to 1 SQCD and what we can say in this example, like applying these results to this particular example. So we mentioned earlier that 40n equals to 1 SQCD with our UN gauge group has this non-invertible R symmetry. And so if we want to compactify to 2 dimensions and preserve some supersymmetry, we clearly want to preserve a U1R symmetry. And so actually, we're going to do some mild deformation of the theory where we add some matter in the determinant and anti-determinant representation of the gauge group with charges such that I preserve my U1R symmetry. So that this is following what was done in these papers. And so basically doing so, I just trade my non-invertible R symmetry for a non-invertible flavor symmetry, where this flavor symmetry acts only on this determinant matter that I added, but it has the same structure. And then I still have a 2 group, so I had the 2 group that involves the SUNF left and SUNF right flavor symmetries of SQCD, but now it also involves my U1R symmetry and this non-invertible symmetry, and some other flavor symmetries in the game. So then we can, then we want to do a particular twist where we introduce an R symmetry flux so that we preserve supersymmetry in 2D. And I'm not going to review the details in this talk, but the statement is that if I do this twist and I look at the reduction in this 0 gauge flux sector, then the result is a 2D n equals to 0, 2 theory in 2 dimensions. And this theory, you can argue, flows to a superconformal fixed point at low energies. And it realizes one of the frames, one of the dual frames of the triality that was discussed in this paper, or in these papers. So that sort of triality has been studied before from 4 dimensions. But let me just kind of summarize what we learned from this perspective from the generalized symmetries. So firstly, you can check explicitly that by reducing our 4D gauge anomalies on the sphere, these particular mixed flavor gauge anomalies we've been talking about, we explicitly match the known 2D gauge anomalies of these 2D 0, 2 quantum field theories. So okay, we indeed see that the anomalies match across this dimensional reduction. Furthermore, our 42 group leads to, as predicted, a symmetry breaking pattern in the 2D theory, which ends up leaving a discrete subgroup, which ends up being a Z2 NF minus NC discrete subgroup, or discrete symmetry of the 2D theory. My 4D non-invertible symmetry, again, we expected that in the 0 gauge flux sector, we would get some invertible symmetry that was at least a Q mod Z type invertible symmetry. And here we can really see that it enhances to the full invertible U1 symmetry. In fact, this U1 mixes with other U1s in the game at the superconformal point to form the superconformal R symmetry of the theory. Furthermore, doing the same game for the Seiberg dual in 4 dimensions, the U NF minus NC theory yields indeed a dual description in 2 dimensions. And you can check that all of the anomalies match across the duality, including this for this discrete symmetry and for an accidental SU2 symmetry from the isometry of the 2-sphere that we can identify from this compactification. And one more comment is that sectors with different gauge flux, as I emphasized, really have different gauge anomalies. Furthermore, they'll generically have different accidental symmetries. So if I'm playing this game in sectors with different gauge flux, I generically do not get 2D dual pairs. And furthermore, I can, as an IR observer, I can say something about the 4D theory I came from because my Tooft anomalies know about this value of the gauge flux. Okay, so I'll just summarize. So in this talk, we explored how some types of one-form symmetry, 2-group structure, and non-invertible chiral symmetry in 4-dimensional quantum field theories reduce on the sphere to 2D in the presence of fluxes. And even when, really the conclusion was that even when the generalized symmetries of the higher dimensional theory are not themselves present in lower dimensions, they still left a distinct imprint on the 2D physics in the form of symmetry-breaking patterns and 't Hooft anomalies that we explored, for example, in this talk, in this SQCD example. And we understood the matching of these mixed gauge flavor anomalies between 4D and 2D in terms of this more robust generalized symmetry structure. So there's a lot more that could be done. For example, this is really just the beginning, starting with this class of gauge theories where we can make very general statements. You should think about more general surfaces for the compactification, more general twists. Maybe looking at the thermal circle would be very interesting. Connecting, of course, with other dimensions, other gauge groups where you might expect some of the generalized symmetry structure to really stay around in lower dimensions. There are various other things you could think about doing, but with that, I think I'll end, and thank you for your attention.